Hello students, so in this lecture we are going to discuss about diffusion. And now is diffusion is a phenomena which is arising out of the transference of mass due to difference in concentration and resulting in a finally in an equilibrium distribution in concentration. Now, this diffusion has got two different types. First one is called the self-diffusion, where when it occurs in one of the single gaseous system, and another one is called the interdiffusion, where two different gases they communicate with each other. Now, the coefficient of diffusion, that is this d value, it is actually the number of molecules that cross unit area, that is when we say that dA is equal to 1 in unit time, that is dt is equal to 1 for unit concentration gradient, that is dN by dL is equal to 0. So this d is given as 1/3 lambda c bar, and it is equal to n by rho. Since lambda is equal to 1/3, so m n c bar lambda is equal to 1/3 rho c bar lambda, and which is the expression for diffusion as obtained from the kinetic theory. So this is the expression of diffusion that we obtained from the kinetic theory. The eta value, that is the viscosity, is 1/3 mn c bar lambda, and it is 1/3 rho c bar lambda, where lambda is the mean free path, that is the distance traveled between two successive pollutions. Now, from Maxwell's equation, we can say that this mean free path is equal to 1 by root 2 pi sigma pi sigma square n. So if you put that into the previous expression, the value of the viscosity turns out to be mc bar divided by 3 root 2 pi sigma square. And since the concentration of the quantities, that is mc bar and sigma, is a function of the pressure, the viscosity appears to be independent of the pressure or density of the gas. So there is the expression of pressure or density of the gas. Now, the departure of the pollution, that is the pressure independent of sigma, is also observed at extremely high pressure, when the mean free path lambda becomes comparable with the molecular diameter, and the transport is not through lambda but through lambda plus sigma cos theta. Now, Engsong showed that the effect of this is to cause this quantity eta by rho vary according to the following relation, that is eta by rho is equal to 1 by 2.54 v by v plus 0.8 plus 0.7614 v by v eta by rho minimum. And so where is the volume of the gas? B is the van der Waals constant, and this quantity is the minimum value of eta by rho, which corresponds to V is equal to 0.8726 into P. Encapsulation has been verified fairly well by Michaels and Gibson, and eta is found to be proportional to the square root of the absolute temperature. So since that is the average of the mean velocity is equal to 8 kT by pi m, which is proportional to root t, but the experiments show that the variation is much more rapid. This is because we have considered the molecules rigid elastic spheres without any mutual intersection. Now, Sutherland in his analysis, he assumed that the molecules are rigid spheres with a weak attractive force that rapidly falls off with distance. Now, the effect of these attractive forces is to increase the collision frequency and is equivalent to a decrease in lambda or increase in sigma, the effective molecular diameter. Now, the results can be correctly expressed in sigma square is substituted by sigma infinity square 1 plus v by t, where p and a are the constants. Sigma infinity is the value of sigma at t is equal to infinity, temperature infinity, and sigma is the molecular diameter at t. So hence the variation of the viscosity with temperature can be expressed as a root t divided by 1 plus v by t, and this is known as the Sutherland's formula.